remember Tutte's one-factor theorem said that a graph has a one-factor, so a subgraph whose degrees are 1 at every vertex. If and only if the number of odd components, maybe this is even, the number of odd components of G minus S for any given S is no bigger than the order of S. Right, and it was trivial, so that is the condition says that this should hold for every S, and Tutte's one-factor theorem says that this is equivalent to the existence of a one-factor in G, and this is clearly necessary. If we do have a one-factor, we cannot have more odd components than vertices in S, because the one-factor has to send at least one edge to S from every odd component. Otherwise, you can't match the vertices up inside that component. So these edges have to be independent, and therefore we need at least as many vertices in S as we have odd components. And Tutte's theorem said that if we have that condition for every S, then indeed there exists a one-factor. Now, the theorem of Gallai-Edmonds that I'm going to show and prove to you in a moment is more general. It's a theorem for all graphs, not just those graphs that satisfy a certain condition. It says that in every graph we can find a particular set S and then say something about these components and about the edges that this S sends to those components. And if it so happens that Tutte's condition holds for our particular S in that stronger theorem, then the stronger theorem will immediately give us a one-factor. So it will imply Tutte's theorem, but it will have a much more structural rather than extremal flavor in total. Okay, we need a few definitions. The first definition is that a graph is factor critical if it doesn't have a one factor, but as soon as you delete any one vertex, it will. So this use of critical is typical in graph theory. You have critically k-chromatic graphs that are not k-chromatic, but once you delete any one vertex, they are. Critically k-connected graphs, same thing. If you delete a vertex, then you get the property that previously you didn't have. And same here. Factor critical means your graph doesn't have a one factor, but delete any one vertex and it will. We'll just need that in the statement of the theorem in a moment. And the other statement that we need is that we call S matchable to G minus S if there is a matching from the vertices of S that covers all the vertices in S, so matches all these vertices to G minus S in such a way that these edges go to different components. All right? So the set of these components here, odd or even, I shall denote by curly C of G minus S, and we say that S is matchable to G minus S if there is a matching from the entire S to G minus S that sends edges to different, pairwise different components. Or similarly, if we contract each of these components, then we get in the bipartite graph between S and that set here, defined in the obvious way from G, we have a complete matching of S. We don't have to cover all the vertices on the right, or even all the components on the right. Okay, so that's that. And here comes the statement of the theorem. So it says that any graph G contains a special set S, not that something should be true for every S, but the theorem says that there exists a particular special set S with some very strong properties. In every G, there exists a set S of vertices with these two properties. S is matchable to G minus S. And the second property is that every component of G minus S, so C element of curly C of G minus S, is factor critical. That's the bulk of the assertion, and then there's one more statement that says that for every such S that satisfies this, so there exists an S satisfying these two things, whenever you take one that does, G has a one factor if and only if we get equality here. Sorry, here it doesn't exist yet. For every such S, there is a one factor if and only if the order of S equals the number of components of the rest. Okay, so let's just see why conditions 1 and 2 imply this last line. If we have a one factor, so give yourselves any such S as in condition little 1 and little 2, if we do have a one factor, then we cannot have more components than elements in S, because S is matchable to these components, right? But also we need at least as many as order S if we have a one factor, because every component there is factor critical. In particular, it has to be odd, because delete any vertex and it will have a one factor, so the rest will be even. But if every component in this set is odd, it must in any one factor send an edge to S. So we get this equality there. And conversely, if we have this equality, then we can easily build a one factor, and we do that by first matching S to these components that are elements of this using 1. And then using 2, we know that these components are factor critical. So we can complete the set of those edges to a 1 factor of G. So it's clear that little 1 and little 2 imply this last statement. And let's just check that Tutte's theorem, the hard direction of Tutte's theorem, does follow from that. What does it say? If for every S we have this inequality, then there's going to be a 1 factor. Well, we use that only for this particular S here. Suppose we have a graph where the Tutte condition holds for every S, throw this theorem on it, and use that assumption just for this particular S, then this implies that we can't have more odd components than S has elements. This implies that we do have that many odd components because all the components are odd. And so we get equality here, and therefore we get a 1 factor as shown a moment ago. So Tutte's theorem does follow, but the theorem has a rather different flavor because it finds in every graph one set S that has certain properties in terms of the components it leaves and how it sends edges to them. And depending on the context, that might imply a 1 factor or not. Okay, so let's prove that theorem. And we do that by induction on the order of G. Now, big warning, the induction starts with the empty graph G. Normally, I just discard the empty graph and say, oh, well, there's an amnesty for the empty graph. Whatever I say need not be true for the empty graph. I don't care. Here, we must care because we're going to base the entire induction on it. So choose the empty graph. Look at the empty graph. The set S that does the job is going to be the empty set, obviously. And the reason it works is that the empty graph is a one factor in itself. It's a subgraph of itself in which every vertex is made of green cheese. In particular, has degree 1. Right? Okay. So that's the induction start. And for the induction step, we measure a particular parameter for the candidates for our special set S, which we're going to call T. And this is D of T, which we define as the number of odd components of G minus that minus its order. So it's Q of G minus T, the number of odd components that deleting T leaves. And the difference between that and order T. So in order to get to 1 factor, there must not be order T many, more than order T many such odd components. So for the T that we're going to be considering, we choose as our S amongst the T for which this is maximum the largest set. Choose as S a T maximizing d of t among these largest. Right? So we first look at all the t's, all the sets of vertices, and we look at their value here. So the value under d of t that measures how much it differs from the Tutte condition that this value should be less than 0. So Tutte condition says this should be at most as big as this. So the Tutte condition says that this is at most 0. Sorry, I said less than, at most 0. And if this is positive, then this measures how far t is away from something satisfying the Tutte condition. So we're trying to look at the worst t that we find. So one that maximizes this. And amongst all these worst t's, we choose the largest one in terms of vertex count. And we call that S. So S is amongst the worst sets for the Tutte condition. It is the biggest. And notice that d of S, I sometimes drop the index g, d of S is going to be at least d of the empty set, of course, because the empty set was a candidate. The value of under d of S is not going to be smaller than that of the empty set, but this is 0. Right? You can just compute that. These are both 0 for the empty set T. So we know that our d of S is going to be at least 0. And right, so questions about this setup? Okay, then I'll prove to you now that this S works. We'll show the first we'll show is that every component of G minus S is odd. Then we'll show that it's not just odd, but factor critical. But we need odd to prove that, so we have to show something weaker first. And then we'll show that S is matchable to C. Okay, and all the little steps that we're going to take in a moment will follow the same idea to get a contradiction. Whenever we increase, or we manage to increase, or no, whenever we increase S by adding some vertices or something, so that Q grows at least as much as the order of S, then we're going to make D bigger if we change it at all. So since it was already maximum for S, we can't make it bigger. And therefore, we have a contradiction because we just made S bigger by adding some vertices. And if this grows at least as much as that does, then we know it grows exactly as much as this does. Then we have another candidate here, but S was the largest amongst them, so our bigger set than S is not going to work there. It will give a contradiction. So that's going to be the strategy in the various cases. And the cases are easy now. So the first thing to prove is that every component is odd. Right, that's easy. We have our S here. Suppose this was even. Just add one of its elements to S. Then this S bar will be 1 bigger than S. So in order to get a contradiction, we want to show that the number of odd components also grows at least by 1. And it does, because this was not an odd component, but after removing that vertex, it's going to be odd. It may not be connected, but an odd graph that is disconnected will still have an odd component. If it just had even components, then it would itself have an even number of vertices. So we get this contradiction, right? Where's the contradiction? We made S bigger, and the number of odd components grew at least as much as the order of S. And that can't be. It cannot grow more than the order of S, because otherwise S would not be one that made this inequality worst, so for which D of S was maximum. So it can only be equal, and if it is equal, so if the number of odd components grows by exactly the same number as the number of vertices in S does, then we still have a contradiction, because amongst all those sets, S was the one of biggest cardinality. Okay, so let's prove that so we know they're all odd. Let's prove they're all factor critical. Suppose one that is not factor critical, this one here. That means there is a little vertex which we can delete so that the rest does not have a 1 factor. Okay, if the rest does not have a 1 factor, then this is witnessed by some S prime just inside this component that leaves more odd components than it has vertices. That's Tutte's theorem. Well, can we use Tutte's theorem? We wanted to imply Tutte's theorem, so we'd better not use Tutte's theorem. But the component is smaller than G, so we can use induction and use the entire theorem, the Gallai-Edmonds theorem, on the component. And as we know, it implies Tutte. So yes, we can use Tutte's theorem, even without assuming it, just assuming it inductively, assuming Gallai-Edmonds inductively. Right, so there exists, if this is not factor critical, then we can delete a vertex, little c, such that c minus little c doesn't have a one factor. Then this is witnessed by this special set S prime. And now we change our big S. Not quite yet. Okay. So let me just write this down in yellow. Q of C prime minus S prime is bigger than order S prime. Or put another way, it's at least order S prime plus 1. I'll write a tentative 1 here. But in fact, this has got to be a 2. And the reason for that is that C prime is even. So this is C prime. So C minus little c. That's this C prime here. That is even. Right? We showed already that all the components are odd. Now we deleted a vertex, so the yellow stuff that remains is even, and therefore we must have a 2 here. Now we get to changing S again, and we'll incorporate S prime and the little vertex C and make that, let's call it T, right? We call that T. And now we want to show the same as before, that the number of odd components grew at least as much as the number of vertices. Well, let's see. How many odd components do we gain? Well, we gain all these odd components here, and they're at least as many as the vertices that we gained from S prime here. In fact, 2 more. That's just as well, because we added this vertex to S as well, so the 2 more melts down to 1 more, and the 1 more we need because we lost the component C, which used to be odd, and now we're not counting it because we're working inside here. Okay, so once more. S grew by order S prime minus 1 for C. Q, the order of odd components, grew by this, which exceeds order S prime by 2. So we're luckily just right again, just fine. Okay, so the number of odd components grew by no less than the number of vertices, and we made our set S bigger, so T is bigger than S. So we have a contradiction. Okay, now third thing we have to prove is that S is matchable to the components, and suppose it isn't, so we have all our components here. If it's not matchable, then by Hall's condition, by the marriage theorem, there is a set on the right, that is the neighborhood of a bigger set on the left. So there exists a set on the left, say, let's call this S prime once more, this is S. We want to show S is matchable to the components. If not, then it has a subset that sees too few neighbors. Okay? But now, we have a problem again, because we can take the rest here as T, right? And now T leaves more, the difference between the odd components and of G minus T and its own order is bigger than it was for the entire S. Why is that? Because all these components here, they were components of G minus S, and they were all odd, but they are still components of G minus T, right? Because T doesn't send any edges there. Sorry. Because S prime doesn't send any edges there, right? So these components here, they don't link up to those components, obviously, because they're components of G minus S. They don't send edges to S prime by definition of their set here. So they are still components of G minus T in their entirety. So they're still odd. And if these are fewer than those, then those are going to be more than those. And we have a contradiction again to the maximality of dt, ds. Okay, and I do want to, those of you that have to leave are welcome to leave. If you can stay another 4 minutes, then maybe you can catch something. This is quite a fundamental observation that follows from the Gallai-Edmonds theorem, and that is that it tells us something about arbitrary largest matchings in a graph. So when we take an arbitrary matching any set of independent edges, and we consider the set S from the Gallai-Edmonds theorem, then we can count the number of edges incident with S, and we can count those not incident with S. And we call those not incident with S KC, and we call those incident with S K big S. And now clearly KS is at most that big, right? You can't have more edges incident in any matching. So both colors together are this matching. You can't have more edges incident in this matching incident with S than S has elements. And we get a similar bound on C, on KC. KC is at most, well, we start with the entire vertex set, minus, these are all odd components, so the green edges miss at least one vertex in there. And of course, they miss S by definition of green. So we have at most that many blue edges. And now, this is true for every matching M. And the canonical out-of-the-box matching that comes with the Gallai-Edmonds theorem, which I showed you right at the beginning, it's still up there. So first, you take edges into that matching by matching S across to the components. That covers the entire S. It goes to the components, and then you fill up the components by using the fact that they're factor critical with other edges. So this satisfies, call it M naught, from the standard matching from Gallai-Edmonds, satisfies these two, both of them, with equality. Right? It does match the entire S across, and then we can fill up all the components, except for one vertex, by green edges, so we do get this with equality. So how many edges are in this? Ks plus Kc edges. That's the maximum number of edges that you can possibly get. But how can now an arbitrary matching that has so many edges sit in the graph? Well, it still has to satisfy these two. And the only way it can satisfy these two is use all these as cross edges. It can't afford to have this. And use all the green edges as I showed them there. So we have shown as a corollary that every maximum size matching in an arbitrary graph has this structure. So that's quite something. That's much, much more than Tutte's theorem says. And that's where I want to close.